Hi, Matthias.
Where are you?
I'm on screen somewhere, but probably not on your screen.
Hello, this is Anne. Okay,
Leonardo, could you
need...
quickly put me on screen for a moment?
Sorry, I didn't get that.
I talked to Leonardo.
I think
we should start, shouldn't we?
I just got a sign that maybe we take some more moments
Okay.
before we start. But now this looks better. So here we are.
Okay.
So welcome back, everyone. This is now the class on algorithmic methods again. And yeah, we're happy to have back Professor Frübis-Krüger. And
just say Anne.
Yeah, I think we can start, right?
Yeah. So today we start again with slides, please.
Can you all hear well what we say? Good.
So today is actually our third talk. The first one was double length. And today we are talking about elimination and normalization as computational tasks. Maybe one word in advance. I'm picking examples from singularities, but I'm talking about algorithms and examples on how to use algorithms to compute what you want to compute. Our goal is to enable you to solve your own problems using OSCA while using knowledge on the algorithms that are in the background. So today you will see things from under the hood of OSCA, and I'll tell you how it works, but they are available in OSCA and you can use them ready-made, but sometimes it's good to know how it works in order to use it. So the first question we are dealing with today is, you have a map, say, from Cm to Cn, given by polynomials f1 to fn. Please don't open it up. So, yes. By polynomials f1 to fn. And we are asking, what is the image of the map? Of course, we want to describe the image by polynomial equations. That's not always possible. You all know if you project a hyperbola to the line, then you get the line without the origin. And that, of course, is not a zero set of a polynomial equation. So in general, we'll not get precisely the image. We'll get the so-called Zariski closure of the image, the smallest variety containing the image. And that's what we want to compute. And to do that, we translate what we have to the algebraic side, as we always do if you want to compute. So we are looking at the corresponding map of polynomial rings, and that map is assigning to xi the image fi of t. And the task here on the algebraic side is to compute the kernel of this ring map. And that is what we are going to do now. And the tool to do that is elimination of variables. Elimination of variables is even older than Grübner basis, but with Grübner basis, it's very convenient to do. So the fact is, if we have such a polynomial ring in two sets of variables and we want to eliminate one of the sets, we can compute a Grübner basis or a standard basis of that ideal with respect to an elimination ordering for t. I'm going to say what that is in a moment. And then we can just pick from those elements of the standard basis, those where the leading term does not contain our variables t that we wanted to eliminate, and we already have a standard basis of the ideal intersected with a subring in the remaining variables. So the main tool at this point is really the elimination ordering for T that we took as the monomial ordering. You know from the last talk that monomial orderings exist and that we are using them for standard basis computations. Now we have to use a special kind of ordering. The ordering has to ensure that the whole polynomial f doesn't involve any monomial in T if and only if its leading monomial doesn't involve any T. That is to say, whenever there is a monomial in the polynomial that involves some T, this has to be bigger than the monomials not involving T, whatever they are. So the conditions on the ordering to be an elimination ordering is first do a comparison only on the degrees in T, and of course 1 needs to be smaller than any T. That is, we need a global ordering in the variables T for the first comparison, completely ignoring the xi variables, and only after that we continue with the other variables. So back to our map. We have a map from C adjoint x1 to xn to C adjoint t1 to tm. So you say we don't have two sets of variables here, but yes we do. If we describe the graph of the map in C adjoint t1 to tm and x1 to xn. So let us denote the ideal of the graph by the generators g1 to gn. And those generators are, of course, xi minus fi of t. And then we can compute the kernel by intersecting this ideal of the graph with the polynomial ring in X. Because if we have a polynomial in this ideal and it doesn't involve t, this means that the corresponding expression in the xi is mapped to something that is 0 on the other side. Matthias, did you say something?
Yes, on the previous slide, the last line, maybe you can go back once. Yeah, here the 1 is less than ti. It's really important. This is about the monomial 1 and the monomial ti. It's not about comparison of real numbers, right? So don't get confused.
Yes. We are talking about conditions on monomial ordering. Indeed. Thanks for pointing that out. So here we see the kernel as the intersection of the ideal of the graph of the map with the corresponding subring. Now let's do that in an example. And here I have picked a space curve with a parameterization t to the 4, t to the 5, t to the 6. And I want to choose an elimination ordering. Obviously, if we want the image of that parameterization, then we need to pick an ordering which first compares only the degrees in t, and then afterwards compares the degrees in the remaining variables x, y, z for the three-dimensional space for the polynomial ring in 3 variables in which we want to have our polynomial ideal later on. So we take lexicographical ordering on t, and after that we take a degree lexicographical ordering on x, y, and z. So we take a block ordering which first compares only on the t and then later on compares on x, y, z if it wasn't clear from the comparison on the t which one is a bigger monomial. Now we write down the ideal of the graph of that parameterization map. we have x minus t to the 4, y minus t to the 5, z minus t to the 6, like you would write it down. But for the computer, the powers in t are the leading monomials when the standard basis is now computed. We get a standard basis with several elements, not just 3. And I didn't put it on this slide because for our argument, it's just important that we can drop all elements from G that involve some T. And then the result is precisely the ideal of the curve that you would expect. That's not restricted to curves here. You can also do that with other examples, and I put here one example for the hands-on session on Wednesday. Now, Matthias, it's your turn to do something with Oscar just for the elimination.
So let me ask, who has been working with images of maps? Some Singularity people do. I know some are from Valencia. Yes? Anybody else? Okay. So have you been using elimination orderings? I think usually you tend to do something with fitting ideals and stuff, right? Okay. So even new to you, what we see now. Can we have my laptop on the screen, please? So this in the beginning is mostly repeating what we just had in the lectures. I hope you can read it. Yes. So down there you find the map that has already been on the slides. Let me find my pointer here. Here I think it is. Do I need to turn it on? Yes, here. So t to the 4, t to the 5, t to the 6. And we need the graph of that map. That means we need to form the ring of the ambient space of the graph. We need to put all the variables in one big pot and start from there. And this is done in the first cell. Let's go through the commands here. It's what Anne had just described. First here we have the, oh, not anymore. Here we have the ideal defining the graph with the expected generators. And this is the this product ordering. It has a priority on the variable t, and then afterwards comes everything else. And let me, this came up in a discussion another day, and I think it's a good way to give you a feeling for what elimination orderings do. When you think of Gauss algorithm in a matrix, and you do this by hand in one of your first years, then you were choosing some column where you want to put zeros everywhere except in one entry. And in elimination ordering, so to say, it works the same way as saying this column I want to clean up, and this column, and this column. And the columns that you want to clean up, they correspond to the variables you want to eliminate. And if you dive a little deeper into Gröbner basis theory, then you will eventually find out that this is, in fact, the generalization of Gauss algorithm. But you don't need to do that. Just take it as an intuition that it's similar to something you already know. So what we do here in the next line is we compute the standard basis with respect to that ordering. And let me delete the last line for the moment to see what the outcome of this standard basis is. Now this is computing. It will take some time, as always, with Julia, in fact. It needs to digest that we want to do something. And this is the standard basis that comes out. So as you can see, most of the elements in the standard basis, they involve this t variable still. Right? And what Anne just said is we need to collect only those elements of the standard basis which do not have a t at all. And by virtue of having chosen an elimination ordering, this will be really a set of generators for the Tarde closure of the image. So, and this has already been done in the last line. So let me put it back in here. This is a little tricky to read, really. And maybe I can just say briefly what this is. This is an anonymous function that sends x to the leading monomial of x. And then I apply this to the whole list small a that came out of the previous command. So let's see what the outcome is. Well, that was not expected. No, that was expected. Sorry, I got a little bit confused. Here is what happens. We need to take only those terms where the leading monomials is not divisible by t. And then it's not really a surprise. It just does an automatic cleaning up of this 7 set of generators that we had before. Right? So the image has an ideal which is generated by 2 elements. We know the dimension cannot really be bigger than 1 because it's the image of a map with a 1-dimensional domain. So we see that the image is what? Does anybody see it? Okay, maybe it's also not so clear where I'm heading. It's a complete intersection, right? Because we have two generators. Okay. Anne, do you want to take over? One question. Let's just wait. You will get a microphone. Everybody, we were asked to have everybody a microphone. It was already on.
How it works for non-quasi-homogeneous cases?
For non-quasi-homogeneous cases, I think because then you may have global contributions to stuff. I think you have to do tricks. You have to work globally, and then you can localize the result again. Because as was already on the slides, and Anne maybe knows more about this, the elimination ordering has to have certain properties. So at least in the first set of variables, you need to choose a global ordering. So with the non-quasi-homogeneous cases, you probably have to do more computation than seems to be necessary and later discard some parts. Anne, can you say something about it?
Yes, you're right. For the first block, we have to work globally. But for the second block, any ordering is fine. So on the X, you can use a local ordering. That's not a problem. But the first block for eliminating needs to be a global ordering because otherwise you don't have the elimination property which says that whenever there is a monomial involving your t variables in there, then also the leading monomial will involve some t. And that is what you need for forming the standard basis so that in the end you get those generators. And as I said, on the X, you are free to choose a local ordering. Does that answer your question?
Yes, he says. Good.
Okay, then I have 2 more remarks on the worksheet. The first remark is up there. Please look at the line where the ordering is defined. You have a degree lexicographical ordering in T, and then it's in the notation multiplied with the degree reverse lexicographical ordering in the other variables. That's the way to do such a block ordering. That's the syntax for it. Just keep in mind that when you need it, you find it on that worksheet. And now further down. Yes, here you have an example of a for loop.
Yeah, it's an implicit for loop, right?
Yes,
Everything is really dense here. I mean, people who do Python, they might know it. We start a list, then we introduce a variable g, and we say for g in a vector, right? So this is an iteration, and then we can even put conditions afterwards. And this is just the condition that the leading monomial must not be divisible by t.
Maybe we should put one simpler for loop in tomorrow's lecture somewhere. So that they also have a for loop to look at.
Yeah, we will have some for loops.
Yeah. So now I'll go back to my lecture, to my slides. And at that point, we found the equations for parameterization. But we also sometimes are dealing with the fact that, for example, for a curve, we would like to have a parameterization. In general, of course, it's not so easy to have something like that. But for curves, there's still a way to get a parameterization, and that is by using normalization. I think many of you know that normalization provides a parameterization. But how does it work? Let us just recall the basics, just to be sure everyone knows what we are talking about. So let A and B be rings, and an element B of the bigger ring is called integral over A if it is a zero of a monic polynomial in the polynomial ring in one variable over A. So what's monic meant to say? It means the leading coefficient, the coefficient of the highest monomial, is 1. So the coefficients of the polynomials are in A, and the leading coefficient is 1, and B is 0 of that polynomial. We are saying something is the integral closure of A in B if it is the set of all elements of B that are integral over A. So for shorthand notation in this lecture, I'll write C of AB, and this is the set of all elements that are integral over A. That's a ring, by the way. And A is called integrally closed or normal, hence the word normalization, if A is its own integral closure in its quotient field. We are also writing A bar for the normalization for the integral closure of A in its quotient field. And I hope that up to that point, I didn't tell you anything new. I just recall things that you heard at some point in the past. Now, our setting is we are in a reduced Noetherian ring. J is an ideal in A, and X is a non-zero divisor for A, being an element of J. And this gives us a very, very useful inclusion of rings that I'm going to explain now. So there is a ring between A and A bar that can be computed. It is the ring of homomorphisms, of A homomorphisms from the ideal J to itself. And this ring of homomorphisms is isomorphic to an ideal quotient times 1 divided by X. That looks very, very surprising at first. How can a homomorphism be isomorphic to some slightly modified ideal quotient? Look at the map down here. If we have a homomorphism phi, then this homomorphism is mapped to phi of X divided by X. And of course, at first glance, you'll say, that's not well defined, that depends on X. But actually, the alinearity of the homomorphism ensures that for any non-zero divisor in J that you're picking, phi of X divided by x is the same as phi of y divided by y. So at this point, we see that the map is indeed well defined, and it can be checked explicitly that we have an isomorphism here. And of course, this ideal quotient times 1 divided by x is contained in the quotient field of A, obviously, since the ideal quotient itself is in A. And it is also not hard to show that it is in the normalization. And this chain of inclusions will be the heart of computing the normalization by Grauert's algorithm, because we'll enlarge step by step A until this process stabilizes, and it stabilizes precisely when we have reached A bar. But we are going to do that slowly, step by step. Another thing that we need here, or that is useful here, is to see that the A homomorphism from J to J, this time seen as A module, is contained in the intersection of the normalization of A with the homomorphisms from J to A, which is in turn contained in the homomorphisms from J to the radical of J. Why is that important? Because if we take J in the beginning to be a radical ideal, then we have the same thing on both sides of the chain of inclusions. That is, we have a tool to also compute the A homomorphisms from J to A intersected with the normalization of A. So as I already said, the idea of the algorithm is our homomorphisms from J to J are indeed computable, because we can compute ideal quotients by Gröbner basis methods, and we can also check that whenever A is not normal, then A will not be the same as the A homomorphisms from J to J. And therefore we enlarge. We take this new ring to be our new A. We enlarge again, and in this way we are moving upwards towards normalization. And of course, the radical is computable, and that is how we get to our normalization. That's the idea of the algorithm. Now, being normal, normality, is a local property. That is, at each point, in the sense of at each prime ideal, you can localize and check whether the ring is local at that point. And if it is local at all points, if it is normal at all points, then it is normal. If there is just one point where it's not normal, then of course the whole ring is not normal. That means also that we can talk about the locus where it is not normal. We can ask, where is it not normal? And that's the so-called non-normal locus. We'll see later on how to compute it. For the moment, it's just important that we have a notation for it. And with that notation, we can formulate Grauert's normality criterion. So we take A, a reduced Noetherian ring, J in A an ideal, such that the ideal contains a non-zero divisor for A, such that the ideal J is radical, and such that the non-normal locus is contained in the vanishing locus of J. If we have picked our ideal J in this way, then A is normal if and only if A is equal to the A homomorphisms from J to J, which can be checked by saying that 1 divided by x times the ideal quotient is A, or in other words, the ideal generated by x equals this ideal quotient. So we have a computable criterion, the computable side is on the right side, to check whether A is normal if we have a good ideal J that we can use for it. Now, to compute the non-normal locus, just as first computational steps that can easily be done, let us take some ideal in the polynomial ring. This ideal should be prime, so that we can be sure that we don't have zero divisors in there. J should be the radical of the ideal of the singular locus of V of I. We know how to compute that. And we just pick an X from J, which is obviously a non-zero divisor in the polynomial ring modulo our prime ideal. And then we can say the non-normal locus of the polynomial ring modulo I is just the locus where the ideal quotient of X quotient with the original ideal quotient vanishes. In other words, it's just at those points, or prime ideals, however you want to see it, where our ideal quotient doesn't equal the ideal generated by X. So let's pick the simplest example in which you see something. It's a cusp. And because we called our non-zero divisor X, I called my X here Z, just to be able to write X equals Z here at the end of the line. So we have the cusp in two variables, plane curve, and our singular locus is of course the origin. Now we want to compute the non-normal locus. That is done by the ideal quotient we had up there. So let's first compute the quotient of Z times J, quotient with J. That is an ideal quotient you could even just do by hand, and you get the ideal generated by Z and by Y squared from it. And now do the other ideal quotient, and you get the ideal generated by Z and Y. Notice that those ideal quotients are all done in the polynomial ring modulo I. They are not done in the polynomial ring. So they have to be understood as ideal quotients over A, not over the polynomial ring. Now, to get from the non-normal locus to the normalization, it's getting a bit more nasty, a bit more technical. So we had seen before that X times J quotient with J also carries the structure of an A module, finitely generated A module, I should say, to be more precise. And we can fix a set of generators as an A module. And for the first generator, we take U0 equals X, the non-zero divisor we had fixed, and then we add the other generators. So to describe our A module homomorphisms from J to J, we then look at a polynomial ring having one variable for each of the generators except U0. U0 corresponds to X, and all those Ti should be thought of as the Ui divided by X, so U0 divided by X is just 1. But it's not just a polynomial ring in those Ti. We also have relations that have to be satisfied so that it really describes this hom A JJ, because of course there are things that happen in there. It carries a ring structure. So we can actually multiply some Ui by some Uj. And this has to be in the A module again. So it has to be possible to express it as a linear combination in here. Please keep in mind that we always have this 1 divided by x, by which the A homomorphisms differ from the ideal quotient. If we take this into account, then we have here ui divided by x times uj divided by x equals the sum over the psi ijk times uk divided by x. Now multiply everything with x squared, then you get another x here that jumps into your formula. So we have those relations that need to be satisfied, and of course we artificially have to put them as relations on our A adjoint T1 to Ts. And this is the ideal. Substitute those ui by t and takes the Cijk from up here and substitutes the uk by tk. And those are the generators of the ideal. And of course, as I already said, u0 divided by x is 1, so t0 should be 1 here. And that's one contribution. The other contribution comes from the fact that, of course, there can be relations among the ui. So if we have relations, then, of course, the other ring, the ring A adjoins the T's, should also have these relations. And therefore, we artificially add those relations to the T's by just transforming the relations among the ui. And of course, in here I wrote all relations, but it is completely sufficient to take just a set of generators for the so-called module of relations or syzygy module of u0 to us. And we get those contributions, and you see they are right computable without problems. Now, in our example, of course, we don't need to take any product with u0 because t0 is 1. So the only thing we need to compute is u1 squared. That's y squared squared. And with our relation z squared minus y cubed, this is the same as z squared y. So we have y times z times u0. And this gives us, for the product contribution, t1 squared minus y, because our y is our psi 0, 1, 1. Now, for the syzygies, we have certain other relations, and we also translate them. That's better to read on the slide than to discuss in a lecture. And in the end, we have this ring here. Now you say, a parametrization. Yes, a parametrization. We still have 3 variables in here, but if you look at the equation to see y minus t1 squared and substituting y by t1 squared, we get z minus t1 cubed. That's precisely the parametrization we have here. It's just hidden in the larger number of variables, and you need to look for it actively at some point. Here we are fine after one step, but usually we have to iterate it, as I said before. So as a last remark, and just a side remark, you cannot just talk about integral closure of rings, you can also talk about integral closure of ideals, and in this case you have to impose the condition that the AI, the coefficients in the polynomial, are all in the ideal itself and not just in the ring. And then, completely similar to the case before, you can talk about the integral closure of I in B. And luckily, you can compute it because the integral closure of A in B is computable. You can compute a product of an ideal with a ring, and you can compute radicals. So in this way, everything is computable for the integral closure of I in quad A. And this is that part of the lecture. And now Matthias has to rush through a bit of examples that we cut short, I think.
All right.
And if you could keep my microphone open, I promise not to interrupt unless it's content of the lecture. So Matthias, go on.
Yeah, I was wondering whether your microphone had been turned off previously, but good, good to know. Then we can now work with that. So I think I picked up the example from the slides again. There was quite a lot on the slides, right? Quite a long story. I mean, on the way to lunch, I was asking around, and it seems to be not a too common thing to know how to compute normalizations. So let's try with the recipe that we just saw. And this is the cusp. I stick with the variable x. Sorry for that, but you will, I mean, z was equal to x also on the slides, kind of, so I hope it's not too confusing. Let's have the cusp here. So what was the next thing? We had this test ideal. I hope it's, I don't say something wrong. We needed one very particular ideal, and we took the radical of the singular locus. Right? And since the singular locus has already been a topic of the previous lectures, I allowed myself to abbreviate this here with the Joker command singular s locus. And no surprises. I mean, everybody knows what the singular locus of the cusp is. It's the origin. So this is our ideal J. And as Anne said before, we have to work over the quotient ring modulo I. That is really the coordinate ring of the cusp singularity, or the whole affine variety defined by this cuspidal function. And you probably saw this before, but in OSCA we need to take quotient rings like this. This will return a pair consisting of our actual quotient ring and the canonical projection map, but we discard the projection map. So now, what's the next step in this recipe? We need to find a non-zero divisor on A, but contained in the ideal J. And we can just go ahead and take the first non-zero divisor that comes to mind, one of the generators of J. So we can start out by setting up the zero ideal in the quotient ring. This seems a little bit complicated. Then we are heading towards the last line. This quotient is actually the command for what we had on the slide. So this translates to that on the slides, right? And this is the set of elements in the ring so that x times j is in I. So for every element in the ideal j, if you multiply it with x, you need to come to the other side. So, and because this OSCA command eats only ideals, we need to translate x into an ideal, and then we can feed it there and compute this quotient. And that needs to be 0, so that x is really a non-zero divisor. And there are many ways to solve this. Of course, we could also do that, working over the original ring R. And I will upload the worksheet later, as usual, so you can check again yourself and take your time. So, next step in the recipe. So we had this homomorphism module, right? The A homomorphisms of J, comma J, and this was isomorphic to this fractional ideal, maybe. So that was on the slides, right? So what we can compute is this part by the same command as before. And that's what I do here in the next cell. And I need to do this in the quotient ring, really. It's important to work in the quotient ring. So we first push over our ideals to the quotient rings. First the J ideal and then X times J. So now we have both at hand. I don't know why this text doesn't compile. So here comes this quotient that we see here. And just this part, just regard it as a formal 1 times x, right? So in here we have now, as you can see on the screen, x and y squared.
Matthias?
Yes?
I would suggest that here we stop at the non-normal locus and don't go all the way to the normalization. Instead, just jump directly to using normalization in OSCAR so that we can still show that within our given time.
Okay. Yeah, in the next step, I made a naive self-attempt to compute the full normalization. But as you saw on the slide, it's a little bit involved. In this case, maybe it's a bit simpler because we only have one non-trivial generator, but you have to take the syzygy relations, you have to take the product relations and cook everything together to have a good normalization meal, and that's too extended and I didn't prepare it. So as Anne said, we can also do everything the very quick way and just compute the normalization of the quotient ring straight away. But now that you saw all the theory, now you have the means, you're well equipped to appropriately interpret the result. And for the full result, or for the full documentation, you can go to the OSCAR website and hopefully learn what you really get in your hands when you type normalization of A. And yeah, maybe Anne, you can explain what we get here and what we do with it from now on.
So actually, we computed on the slides a polynomial ring modulo some ideal, and what we have here is just this multivariate polynomial ring in the new variables t and the old variables x and y. Over the original ground field, we have the ideal generated by the generators that we collected from the product and the syzygy part. And of course, we have a map being the inclusion map of A into its integral closure. And usually, if you look at that stuff, it looks, say, rather involved with many generators. We have a very simple example here, and still we see 4 generators here. So it's hard to look at that. And usually you're just interested in some simplified way to look at it.
So what we see here in number 17, that's the relations of the product relations and the syzygy relations with this new variable T1. Is that right?
Yeah.
Okay. So quite some human non-digestible output. But the machine is okay with it. Good, sorry.
And now we go down to 2 lines further down. Yeah. Now, make it a bit more beautiful there. Yeah. Use that alien part.
Right. Alien part, when you go back to the normal OSCAR, you may see that this command does not exist there. It's exclusively for us here that we can use alien part. Ilimpart is usually part of the singular toolbox, and we brought it to Oscar, and now it tells us how the ideal can be simplified, right? You have this very often. A lot of variables might become superfluous in a quotient ring, and then you can switch to a simpler model. So what does Ilimpart tell us? It tells us if you have this ideal that we put in here, then we can reduce everything to one variable, T1, and everything else can be substituted like that. And
please note that this Ilimpart looks for the smallest sensible way to embed it by looking for linear substitutions that you have in the ideal. It only considers the linear substitutions, nothing else. So it's not a true elimination command.
yeah, you cannot count on it to do proper elimination, or it does not the same job as the elimination orderings, right?
You can count on it to not do elimination. You can count on it to only do the linear eliminations.
Good, but is this the expected output? What do we see from this?
Yes,
the
we
headline
see.
was parametrization. Do you see what's coming out here? Anna, maybe you explain.
You're asking the audience? Matthias, are you asking the audience?
Yes, I was asking widely, but maybe you just explain
Okay.
how this is related to your...
We introduced a new variable t, and now it says x corresponds to t1 cubed, y corresponds to t squared, and t is a variable that we are keeping. So in the end, we have a polynomial ring in one variable, and we see the map x goes to t1 squared, t1 cubed, y goes to t1 squared. So we have precisely the parametrization that we would expect from the algebraic side. Of course, it's not the geometric side with which I started at the beginning of the lecture, but it's the map of rings. And at that point, I think our time is up. Isn't it, Matthias?
Right, I just got a sign that we must stop now. But we will continue tomorrow. So, thank you. Good, and I am afraid we have no time for questions right now, but I'll be around, and otherwise tomorrow we continue. Is that okay with you, Anne?
That's okay with me. Remember, we have leftovers from today. We have leftovers from last Wednesday that we'll discuss tomorrow and see how far we get.
Okay.
So should I start? Okay, there's no chairman. So I thank the organizer for. No, it's okay. I know myself. So I thank the organizer for this nice school and for maintaining this session here in San Carlos. So Mihai asked me to give a lecture on index theorem for Euler characteristic of a real mineral fiber. So that's what I'm going to do today. So it's very basic. It's more or less the same thing. I already explained 10 years ago in a course here, in a summer school here, and also in Salvador in 2015. And maybe on Wednesday I will talk about some more recent work. So I first start by introducing the degree, the broader degree of a map. So you take M, compact, oriented manifold, smooth. And N is a connected, oriented, smooth manifold. And they have the same dimension. I say they have the same dimension. And I consider a smooth mapping between F and M and N. I call it F. So it's smooth. And to each regular point, I can associate a sign, which is just the sign of the differential. So I take M, a regular point of F. So his differential is just an isomorphism between two oriented vector space. So I say that the sign of X is +1 if the differential preserves the orientation, and it's -1 if the differential reverse the orientation. So sign of dfx is +1 if F preserves orientation, and -1 if it reverses orientation. Okay. So now I will define the degree of F at a regular value of N. So definition, I take Y in N a regular value. And so the degree of F at Y is just the sum of these signs over all the pre-images of Y. So the sum of the sign of the differential of X, where X is in the pre-image of Y. So this is well defined because this is compact. So let me make a picture. So imagine this is N, and M is something like that. Non, c'est pas ça que je voulais faire. This is M. So this is N, the circle. And my mapping is just the radial projection onto N, the center of M. Okay, and here is F, Y, And we have we have 3 pre-images here. 1, 1, 1. So here the orientation is preserved, so the sign is +1. Here the orientation is reversed, -1, and here it is +1. So here the degree of f at y is +1. Okay. So the theorem is that this does not depend on the choice of the regular value. So theorem, the degree of f at y does not depend on the choice of the regular value. Does not depend on y, let's say. And we call it the Brouwer degree, or the mapping degree, or the topological degree of f. So definition. So the degree of f is just the degree of f at any regular value of f. Okay, so one property, first property, which is important, very important, let's say. So if you have 2 homotopic map, then the degree is the same. This is very important. So if f is homotopic to G, then the 2 mappings have the same degree. Okay. So, okay. So now let me give some examples. So here we have one example here. So you see that if I pick another regular value here, then it has only 1 pre-image, and the orientation is 1. So we see here we see that the degree of f at z is 1. Okay, so let me give other examples. So first example. So this is similar to this one, but here M would be a kind of a bin, like that. N is the same, is a circle here, and the mapping is the same. So what is the degree of this map? Yes, 0. Why? Here you see that this point has 2 pre-images. Here the sign is +1, here is -1, so 0. But you see that here, for example, it has no pre-images, so the degree is 0. Okay. So let me write a more sophisticated example. So imagine you have a knot in R3, something like that. So it is oriented. And to each point, I can associate a unit tangent vector, which gives the orientation. And the mapping is sending the unit tangent vector to the sphere. Okay. For example, this one, maybe. We send here. So what is the degree here? Yes, this is 2. You see, take for example, take this vector here. Yeah, it has 1 image here and another one here. And you see the orientation is preserved. So here the degree is 2. So this is also called, this degree is called the rotational number of the curves. It is a number of loops you make around the sphere when you make one loop around the curve, along the curves. Okay. So another example. So very easy. You consider this the mapping Ri from the sphere to itself, and just you change the ES coordinates xi to minus xi. So what is the degree here? Yeah, you can make a picture here. The two sphere. The point here is sent here, and you see the orientation is reversed. So this is -1. So another example, if you consider S1 in C, and you consider the mapping Z is sent to Z to the M, with them a non-zero integer. So the degree will be M. This is the number of loops you make when you go around the circle. So here the degree is M. Good. So now maybe we will prove one of these examples during the exercise session. So, okay, another property. So the degree of the composition is just the product of the degrees. So it's quite easy from the definition. And so we can deduce the degree of the antipodal map. So this is a map from Sn to Sn that send x to minus x. So this is the antipodal map. So what is the degree of the antipodal map? Using the example 2 and property 4. Yes? Yes? You just apply this mapping to each coordinate. So it's just you compose all the array. So degree of the antipodal map is -1 to the n+1. Okay. So now I will present a way to compute the degree when we have an hypersurface in Rn. So this is a particular case. So imagine you have M, so smooth oriented, smooth compact connected. So connected is important. So compact in Rn, an hypersurface. So this is an hypersurface in Rn. So by Jordan theorem, it bounds an open subset of Rn. So M is equal to the boundary of D bar, where D is an open connected set of Rn. So where D is open and connected, unbounded, of course. So this is the picture. So this is M, and this is here inside. This is D. So we can orientate M as a boundary of D, because D is oriented as an open subset of Rn. So it gives an orientation of M, like that. And the orientation is that I choose the normal, outward normal vector. And I choose the orientation in such a way that this gives a direct basis of Rn. So this is the situation. Now, I consider F a mapping from D bar to Rn, this mapping, and I assume that it does not vanish on M. So F does not vanish on M. And also I assume that it has inside D a finite number of zero, which are all non-degenerate. So here I have the zero of F, or here, finite number, and they are non-degenerate. So this first does not, and second hypothesis, F has inside D a finite number of zeros that I will call P1 Pk. And I assume that they are non-degenerate. This means that the differential of F does not vanish. Okay. No more, it's not singular. Yes, and they are all non-degenerate. So I can consider the mapping from M to the unit sphere, F divided by its norm. This gives a mapping from M to the unit sphere. I will call this mapping I don't know. So I consider this mapping, F divided by its norm. It's a mapping from F to the unit sphere. So it has a degree, and we can compute the degree thanks to the zero here that are inside D. So the formula is that the degree of this mapping, this is just the sum of all the signs of the differential of F at the point Pi. Okay. Sum. Okay, this is in the case of an hypersurface of Rn, this is a nice way to compute the degree. Okay, so when did I start? I don't remember yet. There's no Sherman, no rule. This is anarchy. So now I will just remind Eisenbud-Levin-Kimchashvili formula that Dirk presented in one of his lectures. I will just recall the theorem just to stress on the fact that we can compute, in some situation, we can compute a degree in an algebraic way. Okay. So This is paragraph 2. So local degree and the Eisenbud-Levin-Kimchashvili formula. So I will write a ELK formula. So I take a C-infinity map germ from Rn to Rn. So F is F1, Fn. So it's a map germ. Is infinity smooth. So if it has an isolated zero at the origin, then we can consider the degree of the f divided by its norm on a small sphere. So the degree at the origin, the local degree of f at 0 is the degree of f normalized from a small sphere to the unit sphere. Okay, this is the local degree at the origin. This is also the Poincaré index. You can consider this as this is the local form of a vector field. And so this is also a Poincaré index of this vector field. So the Eisenbud-Levin-Kimchashvili formula is an algebraic formula to compute this degree. So I consider QF the local algebra. So this algebra has already appeared in several talks in this school. So this is the germ of C-infinity function divided by the ideal generated by the coordinate of f. So this is the local algebra. And the Eisenbud-Levin-Kimchashvili formula gives a way to compute the degree as a signature on this algebra. So let me remind the theorem. So it was proved in I think 77. So there are two papers, one by Kimchashvili in a Russian journal, and one by Eisenbud and Levin. So I assume that this algebra is finite dimensional as a vector space. Okay. Then 0 is isolated in f minus 1 of 0, and okay. I think I have time. So 1, 2, the Jacobian of f does not vanish in QF. And 3, if I take phi linear form, such that phi applied to Jacobian is strictly positive, and I construct bilinear form capital Phi, symmetric bilinear form by so maybe F is not good, G and H, by applying the product GI to phi. Then this gives a non-degenerate bilinear form, and its signature is the degree at 0 of f. So then phi So this is symmetric and bilinear. So a capital Phi is non-degenerate. And its signature is the degree at the origin of F. Okay, so Dirk already presented this formula, and he gave a very complicated example. So now what I'm going to do is to present a formula for the Euler characteristic of the real minor fiber in terms of the degree. Okay. So this is Kim-Shashvili formula. So the Kim-Shashvili formula. So here I will restrict myself to the analytic case. So I consider F an analytic function germ. And I suppose that it has an isolated singularity at the origin. So what is Kim-Shashvili formula? It's a real counterpart of the formula that relates the Euler characteristic of a complex minor fiber to the minor number, let's say. So theorem. Kim-Shashvili. Okay, so what is the formula? Maybe I should write it here. So under this assumption, so the Euler characteristic of f minus 1 of delta intersected with ball of radius epsilon is 1 minus, so there is a sign here, sign of minus delta to the n times the degree of the gradient at the origin of the gradient of f. Okay, where as usual we take a delta and epsilon small. Okay, so I will give the proof. It is very similar to what Dirk explained in the complex case last week. So I will work in a small neighborhood of the origin where f is defined. So I take U, a small open neighborhood of 0. Of 0, and we will work. I assume that f is defined on U. So what I do now, I perturbed this function into a Morse function. So we perturb f into a Morse function f tilde. So if it is Morse, it has a finite number of critical points, and they are non-degenerate. So with critical points, P1, Pk. Okay. So now I can make a picture. So you will recognize the picture. So this is my zero river, and here I have the negative fiber. Here the positive, and I work in a small neighborhood here. This is U. So this is so maybe I will choose a delta positive first. So here, let's say this is I will say this is a B epsilon. And here, this is f minus 1 of delta. And here it's high, not too far from the origin. We have the critical point of f tilde, the deformation of f. Okay. So this is the same picture as Dirk did last week, I think. So now I apply Morse theory. So I take delta positive, and then I apply a Morse theory. So what it gives that the Euler characteristic of the tube, f minus 1 of minus delta intersected with the ball, minus the Euler characteristic of f minus 1 of minus delta intersected by B epsilon. So this is equal, just by Morse theory, to the sum from for y from 1 to k of the sign of the differentials of f tilde at pi. Okay. This is Morse theory. Okay. So you know here, this is this thing. So I have to prove that this is 1, and that this is the degree, the local degree of f. So why this thing is 1? So the idea you can, following the trajectory of the gradient, you can retract the tube to the transcentral fiber. And since it's a local analytic set, it is contractible, and it contracts to a point. So this gives a restriction to the central fiber. And the central fiber is just, since it's an analytic set, it has a conic structure, local conic structure. So So first step. Yes. So the tube f minus 1 of the interval minus delta delta intersected with ball. So retracts to the central fiber. And this is a cone. So it has a Euler characteristic 1. So which is a cone over the link. So it has a Euler characteristic 1. So it has a Euler characteristic 1. So this is this part is 1. Okay. So now we have to prove that this is the degree of f of the gradient of f at the origin, but this is not too difficult. This is an application of example 6 I gave. You know how to compute the degree of a mapping defined on an hypersurface. So this is by example 6. This sum is just the degree of the gradient, the normalized gradient of f tilde. But then, if I choose f tilde close to f, then the mapping are homotopic. So by example 6, this sum is a degree of this mapping, normalized gradient of f tilde. Yes. This is exactly what I explained in example 6. But if f tilde is close enough to f, then this is homotopic to the gradient of the normalized gradient of f. And then we see that it is the degree of at the origin of the gradient of f. But then this mapping is homotopic to the normalized gradient of f around the small sphere. Okay. So this degree is equal to this degree, and this is a local degree of the gradient of f. So the degree of this mapping is exactly is what we wanted. So this gives the result for the negative minor fiber. To get the result for the positive, you apply the same argument to minus f. Okay, nothing difficult. So this is what we call the real minor fiber, and you see that there are two of them. So definition. It's called depending on the sign of delta. Positive, negative or positive. Sometimes we say also left or right. Real minor fiber. Okay. I just finished with a corollary. Then I think I have enough material for exercise. Just a corollary, an application of the Kim-Shashvili formula to get a formula for the order characteristic of links. So corollary is due to Arnold and Wall. It's not difficult. Arnold and Wall in different papers. So we still work under the same hypothesis, and we have the order characteristic of the set F less than 0, of the link of the set F less than 0 is 1 minus the degree, the local degree of the gradient, and we have a similar result for the positive part. It is 1 plus, here there is a minus 1 to the n plus 1, the local degree of the gradient of f. So how do we prove that? So this is just this is a deformation argument that appears in first in Milnor's book. So by a deformation argument due to Milnor, then the negative, maybe I should make a picture. Yes. So here is my negative fiber. I intersect with the ball sphere. Then what we do is that we can, using a vector field, appropriate vector field, we can deform, we can push the minor fiber, the negative minor fiber, this part in orange, to this part here. They are homeomorphic by integrating a vector field. So here, the part in orange. So this is homeomorphic to this part. But then here, since we have an isolated singularity, here the intersection is transverse. So here we can push this to this. Okay. So by deformation, so the negative minor fiber is homeomorphic to f smaller than minus delta intersected with the sphere. And this part is homeomorphic to f smaller than 0, because here we have transverse intersection here. And this is homeomorphic to it's negative f smaller than 0 intersected by. Okay. So in the exercise section, we may make some computation of a degree and some computation of Euler characteristics. And then on Wednesday, I will give generalization of this result to non-isolated singularity case. Okay, so I stop here. Questions? Yes. Which one?
So the last corollary, if you take n equal 2, is a plane curve and just count the number of branches, no?
I think
So 1 minus the degree of the gradient is maybe the number of half branches, or the number of branches, no?
you have to go a bit further to compute the Euler characteristic of the link. Yes. The number
But the link is a finite number of points, no? In that case.
No,
n equal 2?
the link is here, and the number of branches is here. Is those those 2 points. But you can apply Maillard-Vietoris and you get. This was an exercise.
Okay. Thank you.
Roberto.
In this corollary, nor on the previous theorem, I don't see the difference in the sign. Can you explain that? Whether it's negative or positive, something changes. Where is this change in the proof?
Here. But the change is because if you take the positive Miller fiber, you have the change in the sign.
Sorry, can you repeat?
If you take the Euler character in the Kim-Chashvili formula, there is a change of sign in the formula for the positive.
In the theorem.
Yes.
Yes, but I don't see that part neither.
You mean in the
Yeah, in the proof, I don't see where does the sign play a role.
In the Kim-Chashvili formula?
Yes.
Because if you apply to minus f to get the formula for f positive f minus this is minus f minus 1 of minus delta. Okay. Okay. So you apply the previous case to minus s. So you get that. Is the one of the gradient of minus f. So here, this is minus the gradient of f, and the degree of this degree, it's by you compose with the composition of the gradient of f with the antipodal map. So that's why you get a multiplication by the degree of the antipodal map. So we have an exercise session. So you have half an hour to revise. So, let's start the exercise session. So I have prepared 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 exercises. So we won't have enough time for all of them. So I will start with a very easy one. So imagine you have a mapping from M to N, so with a good hypothesis in order to define the degree, but M is not compact. So what is the degree of F? No, it is always finite. M is compact, always, but N. So Juanjo knows the result, but he's not allowed to give the answer. So M is not compact. Why? Yes, it is. If M is compact, F of M is compact. So F is not surjective. If a mapping which is not surjective has a degree 0. So F of M is compact. So it is strictly included in N. So F is not surjective. And this implies that the degree is 0. Okay, so it was very easy. So do you want me to prove the formula? Degree of G composed with F is the degree of G times degree of F, or you want to skip to another exercise? You want another? Maybe. So we make we'll compute the degree of the mapping that so Rn that change the last coordinate to its opposite. So we saw that the degree was -1. So I will explain it. It's not difficult, but I will give a kind of a rigorous proof. You can't read this N here. So this is a sphere, and I will work with the north and the north pole and the south pole. So the preimages of the south pole is just the north pole. And we just have to show that this mapping reverses the orientation. This is just this. So this is a tangent space at the north pole. The tangent space at the south pole. So this is here the norm outward pointing unit normal vector. Okay, so a basis in the space here is direct if when I add the loss vector, the normal vector, which is En, it gives a direct basis of Rn. So using canonical notation is a direct basis of Tn S minus 1. But you see, the tangent space is the same, but the orientation is different. Because here I want to, a basis here is direct for the tangent plane, the tangent space. If when we add minus En, we have a direct basis of Rn. So here we have that E1 En minus 1 is a maybe we don't say direct positive, let's say basis, negative basis of TS. Yes. Okay. So now, what is a differential? This is a linear map. So the differential is itself, and the restriction, the differential of Rn restricted to Tn to the tangent space is already the same mapping. So drn is Rn everywhere because Rn is a linear mapping. And so it's a restriction of a linear mapping, let's say. And so drn drn of EI is EI for I from 1 to n minus 1, drn applied at n. Okay. So the differential maps a positive basis to a negative basis. So it reverses the orientation. So the degree is minus 1. So drn EI, drn at n sends a positive basis to a negative 1. So it reverses the orientation. And the degree of Rn is just is minus 1. Okay. It's okay. It's a very simple example. So, okay, so now so let's compute some Euler characteristics. Oh, maybe. I will give you, before computing some Euler characteristics of mineral fibers, we will compute, for fun, we will compute a local degree. So F and so F x1, x2, x3, x4 is equal to x1 square plus x2 square plus x3 square minus x1 square minus x2 square plus x3 square plus x4 square, and then x2, x3, x2, x4. So it has an isolated 0 at the origin, and what is the degree? To compute the local degree. So no idea, no intuition. So I will give you some hint, just to compute this kind of things. The idea is to use the criterion I gave, example 6. So we have that the degree, the local degree is equal to the following degree. Okay. But here I cannot use the criterion 6, example 6, because I don't know if it's degenerate. In general, it's degenerate. But I can make a small perturbation, perturbate by a regular value, a small regular value. If delta is small enough comparated to epsilon. And here you choose delta, a regular value of f, where delta is a regular value of f. And so this is just to compute this degree, you just have to find the preimage of delta by f inside the ball and compute the sign of the determinants of the differential. So this is equal to here we are in this situation. And here we have non-degenerate zeros. So this is the sum of the signs of Jacobian. But pi, where pi are inverse image of delta, and pi are in the ball, the open ball. Okay. So now the idea to compute this is the interior, is to choose a regular value and find its preimages inside the small ball. Okay, here I think I put. I will keep the notation of the course. So which regular value delta can we choose to get something easy? Here, when you have product here, what can we put to simplify it for the last coordinates? Something easy. The idea here is to put a 0. x2, x3 equal to 0, x2, x4 equal to 0. And then here you will get 0. So either x2 is 0, either x3 or x4 is 0. Then here you will get 0. If x3 or x4 are 0, then if I put 0 here, I will have x1 and x2 equals 0. And here I put something negative, then there will be no preimages. And so the degree would be 0. So you take delta. I take, yes, so take delta equal 0, so beta positive. And we look for the preimages of delta. So equal to delta, so you have this system, x1 square plus x2 square plus x3 square minus x4 square is 0. X1 square is equal to minus beta, and then x2, x3 is 0, x2, x4 is 0. So here we have two cases. First case, x2 is 0. Then this implies that this is positive and this is strictly negative, so it's not possible. Then x1 square plus x3 square plus x4 square is minus beta. This is impossible. And if x2 is not 0, then x3 and x4 are 0. And then we have x1 square plus x2 square equals 0, and x1 square plus x2 square minus equals minus beta. And this is not possible because this implies 0, x1 equals 0. Okay. So this is empty. So f minus 1 of delta is empty. And so the degree is 0. Okay. So let's do another example with this, the same method. Yes? Here it is a regular value because it has no preimages. In this case, it's a regular value. So let's do an example with a non-empty preimage. This is more interesting. So it's just a small modification here. G. So it's x1, x2 plus x3, x4, x1 square minus x2 squared. Yes, it's x3 square, x4 square, and then, okay, minus x2, x3, x2, x4. Okay. So we'll do the same. We will use the same value and look for the inverse image of delta by G. So I keep the same value delta G. Here, what change? The first line is different. x1, x2 plus x3, x4 equals 0. And then here. So here, the first line, this is, I don't have to erase it because this is still true. If x2 is 0, you have something greater than 0 and something negative. So, impossible. So then, if x2 is 0, x3 and x4 are 0, and then I get x1, x2. Yes, so this is 0, x1, x2, 0, and x1 squared minus x2 squared equals minus beta. So this implies that x1 is 0. And so I end up with x2 squared equal beta. So x2 is a square root or square root of beta or minus the square root. So this time we have two pre-images. So we are, as you said, Alex, we have to check that they are regular values and then compute the sign of the differential. Here, the computation are quite easy. Let's compute the differential of K. So what is the differential? Yes, that's it. So here we have two pre-images. Gp is equal to delta. It is equivalent to P equals 0 square root of beta 0, 0, or P 0 minus square root and 0, 0. So the differential, so it's very easy to compute the differential of G. So x2, x1, x4, x3, then 2x1, 2x2, minus 2x2, 2x3, 2x4, and then minus x3, minus x2, 0, and then x4, 0, x2. So you see that at the point P, at these two points, you just get a diagonal matrix. So dg at 0 square root beta 0, 0 minus 2 square root minus 2 square root, and then everywhere you have 0, everywhere else, and then square root minus square root of beta 0, 0. So you see that the determinant is positive for both value. So the degree is 2. Okay. So we see that the determinant here I can put plus minus is positive. So the local degree is 2. Okay. That's not complicated. So if you have understood this, you can make the following exercise. by yourself. So compute. So I don't know. So we consider these two functions. So x2 plus y square plus or minus z to the k plus 1, where k is a non-negative integer. Consider this function. So what is compute the Euler characteristic of the minor fiber. The several, there are 4 of them now. Depending on the plus or minus here, and then plus or minus. So how does it work? Using, of course, the idea is to use a computer degree, because you can, it's not too difficult to compute by n. But here we want to apply what we did in the lecture before, what we saw. So how do we compute these Euler characteristics? Not exactly the last corollary. Yeah, the theorem before. So we just have to compute the degree at the origin of the gradient. So what is the gradient of f plus or minus? So this is 2x, 2y, and plus minus 1, k plus 1 to the times z to the k. So what is the degree if k, first case, there is an easy case? So what is the easy case? There is an easy case when we want to compute this degree. Which one? To compute. Then we will apply, but the question is to compute this in this degree. So there is an easy case. Okay, the second case is not difficult, neither, but very easy case. Well, yes, that's it. If k is even, this is not surjective. So the degree is 0. So if k is even, then 0, 0 minus beta, where beta is strictly positive, has no preimage. So the degree would be 0. And then you apply Kim-Shashvili formula, and you get that everything is equal to 1. So this implies that the degree at the origin is 0, and by Kim-Shashvili formula, here you can put whatever you want, plus minus, this will be 1. Okay. So what? Yes. Questions? No. So what about the case K odd? Here we can take same. We can even take beta positive, and we have just one pre-images, and we compute the sign, and it's not difficult to compute. So if K is odd, then maybe I'll make yes. I will distinguish between F plus and F minus. So if K is odd, so let's compute the inverse image of 0, 0, beta positive. So we have, yes, 2x equals 0, 2y 0, k plus 1, z to the k is equal to delta. So we just have one pre-image. Okay. X is 0, y is 0, and z is delta. Okay. And then you make the compute the differential at this point, and you see that is a positive. I guess. Yes. Yes, I changed the delta beta to delta. And so we have just one pre-image. And then we just have to compute the sign of the differential of the Jacobian determinant. And this is very easy. So differential of so 2x divided 2. Okay, so yes. Okay. So you see here, the exponent is even. So the sign is always positive. The sign of the determinant. If z is not 0. So here we have that. So sign. So the determinant of the differential at P is exactly K times K plus 1 times this thing. And I take the exponent K plus 2. So this is positive. And then, because this is even. So the degree is plus 1. Okay. So I think this is the same. If for f minus, what happened? Yes, for f minus, I will have just a minus here, minus sign, and then the sign would be negative. Okay. So for f minus, here I have minus, here minus. Here I should put this. Minus. Here I just have a minus sign here. And so minus 1. And then you apply Kim-Chashvili formula, and then you get that it's 0 or 2. Okay. Okay, right. So maybe something more interesting. Tom Sebastiani formula in the real case. It's a bit more general. And then we will finish with that. So Tom Sebastiani. I don't remember the number. Maybe 6 or 5. Sebastiani. So you take two germ, analytic germ, one from Rn to R, and one from Rp to R. So with isolated singularity, isolated critical point. Then you construct a map from Rn plus P by adding F and G. So I call it capital F. And xy is sent to fx plus gy. And then show that one minus the negative, the error characteristic of the negative minor fiber of capital F is one minus the Euler characteristic of small f, of the negative fiber of small f, times 1 minus the Euler characteristic of the negative minor fiber of J. P here. And P. So there are many parentheses. Yes, maybe I made a mistake. Well, it's okay. So, what is the strategy? If you have understood, what is the strategy? What is the strategy to prove this Tom-Sebastiani formula? Kim-Chajui, yes. Yes, this is you just prove that the degree of this map at the origin is a product. And then this is just reformulating. This is a reformulation of the fact that the degree at the origin of capital F is a product of the degree of F. And this is just. And let us prove that. Oh, I have just 5 minutes only. So the proof is easy. It's an application of Kim-Chajui formula. First step. So this is not the degree, I'm sorry, not the degree of F, but of the gradient of F. We have this. First step, and then apply Kim-Chajui. So we will prove one, and then stop. Okay. So 1. So the gradient is just the sum of the two gradients. So gradient of capital F x y is the sum of gradient of f applied at y plus gradient of j gradient fx and plus gradient of gy. So now, what do I do? There is coming, so we have to finish in 2 minutes. I have to choose a good regular value for f, capital F. Which one will I choose? Yeah, you take a regular value for gradient of f in Rn, a regular value for gradient of j, and you concatenate. So say I take epsilon. No, maybe epsilon is not a good notation because it's a radius of the sphere. Let's say delta, regular value of f. So yeah, delta prime of g. So it has pre-image Q1, QL. And then the delta prime is a regular value for gradient of capital F. And the pre-images are just Py, Qj. You apply the formula and then you get the result. So I put theta for delta y. So the pre-images of delta by the gradient of capital F are pi qj for I 1 to k, j 1 to L. That's it. And then you look at the determinant of the gradient of capital F at eta at pi qj, and you see that this is just a block matrix. Okay, so you have the sign. The sign of the differential is just the product of the sign. You make the sum and you factorize, and you get the result. Okay, so sign of the differential is just the sign times so you compute the sum at each the sum of this, then you can factorize, and you get the result. So I stop here. Do you have questions? No. Okay.
On. That's all. So that's better. Thanks, everybody, for coming. The idea here is this is to give you a chance to ask any questions you might have about the notes or about the exercises. And I've also selected a few problems to go over. The idea is to try to give you a better feeling about integral closure. That is, what is in the integral closure of an ideal? And also to show you a little bit how the tools are used. Okay. If we have an ideal in a local ring, then one of the conditions we had for this to be in the integral closure of I involve curves. So let's see, we had XX. What did we expect to happen if H was in the integral closure of I? What does it have to do with these curves? Well, what we want to have happen is that if I look at H composed with phi, then that should be in the ideal pullback of the ideal. Okay. So now let's see an interesting theoretical example of how this is used. Problem. Show F is contained in the maximal ideal times the Jacobian ideal of F bar for all F. Is this true? True or false? What do you think? What's an example where it's true? Yeah, something's weighted homogeneous, perhaps, or homogeneous. What's an example where it's false? Almost everything. False in general. Okay, but we can prove this anyway. At least F is always in the integral closure of MNJF. And so let's see how we do that. Here, a little bit of notation is helpful. Let's use. Given phi, mapping Cn0 into XX, I'm going to write the order of F with respect to phi is equal to K, where F composed with phi is equal to T to the K times sum H, where H is a unit. Okay, so let's start the proof. Let's consider the derivative of f composed with phi with respect to t. We're given that the order of f along phi is k. Oh, yeah, in this example, you're right. In this example, well, okay. Yeah. I was trying to do a general definition, but we can put C. Oh, I see. C. Yeah, good. C to X. Thank you. Yeah, phi goes from C to X, right? In this case, X is Cn. Okay. So we know by the chain rule that this is equal to the sum of zi primes as functions of t times the partial of f with respect to zi composed with phi of t. Here, zi, I'm thinking of phi of t as being z1 of t, zn of t, okay? So I just take the derivative of the components. Now the order of df composed of phi dt, well, that is k minus 1. How about the order of the other side of the equation? Well, if I want to look at the order of this summation here, then I know that that order has to be greater than or equal to the nth of the orders of the terms. Okay, we have this much. And here, I didn't put it in, but there should have been here, is the order with respect to phi of this quantity here. Yeah. Well, notice that the order with respect to phi of this quantity let's see, so say the, oh, okay, so the, and I guess I can leave that out. This is clearly going to be equal to the order of zi minus 1 because I just took the derivative. And then this is something that we're interested in. And so we get that the k minus 1 is equal to the order of some zi minus 1 plus the order of partial f with respect to zi for some I. And so k is equal to the order of zi times the order of the partial of f with respect to zi. And then we're done. We've shown that the order of f along phi is equal to, at least, well, is less than or equal to the order of some term here. Oops, is greater than or equal to the order of some term here. And so this implies that f is actually contained in the integral closure of something a little bit stronger. Okay, so I have something a little bit better. Question? So let's see here. So we had that this was greater than this. So I took the smallest one here. And so, So to get this one here, you want to realize that the order of the product is the sum of the orders. Right? So if we have the order of t to the k times t to the l, then that's the order of t to the k plus l is equal to k plus l. So here we have the order of this one. Now the order of this one is equal to the order of the original minus 1 because we took the derivative. So this is actually greater than or equal to here, bringing that over. Okay. Here's a corollary, which is a couple of corollaries actually. Question? How do I know that what? Okay, well, let's just think about it. Zi is equal to the ith component of phi. And so phi is a power series. So it's going to be, well, I can always write it as TL times a unit. And now if I take the derivative with respect to t, I have L times t to the L minus 1 times a unit plus t to the L times h prime of t. Okay, so this is a unit, and so this is the lowest order term. It's certainly less than t to the L. I'm sorry, what did you say? Oh, no, you don't know which one it is, but it's one of them. But the point is that all of these derivatives, all of these component functions have their order dropped by 1 when you take the derivative, so it doesn't really matter which one it is. Okay, so we were looking at some corollaries here. Now this is obvious because this is equal to the integral closure of the ideal generated by F plus the Jacobian ideal. And we've just gotten through showing that this is contained in here, so that's done. And this has another nice corollary. This is one, and then two is that the multiplicity of TKE of F is equal to the multiplicity of the Jacobian ideal, which is the Milnor number of F. So we know that the codimension of this guy is the Torino number. When you shift to the multiplicity, you get the Milnor number. Whenever two ideals have the same multiplicities, whenever two ideals have the same integral closures, they have the same multiplicities. All right. Now let's look at some computations, which I hope will allow us to compute a large piece of the integral closure of an ideal in certain cases. So here's the relatively simple example I want to start with. And JF bar contains H in ON. Actually, it's O2 we're working in here. Where the weight of H is greater than or equal to AB, and X is B, and the weight of Y is A. So this problem is the first step in trying to replace the computations by combinatorics. Okay, so the Jacobian ideal of F is just the ideal generated by X to the A, Y to the B. And we've seen how you can plot the two monomials that appear there in a quadrant. And so we have, this is a comma 0. It's the x-axis, and the y-axis up here as usual. And here we might have 0b. And I want to draw the line that connects those 2 points. Now, one thing I recognize is that if I want to calculate the order of phi of a monomial like x to the a, this is the same thing as calculating the order of x to the a with respect to the initial parts of phi. If phi is equal to t to the k1, h1 of t, t to the k2, h2 of t, hi units, then the initial part of phi is t to the k1, t to the k2. We can see if I compose x to the a with this, the only term that really matters is this front term, the initial term. The rest is a unit. Now, if I have a monomial, and I want to calculate its order with respect to phi, then it's easy enough to see what I get. I'm going to get an I times K1 and a J times K2. So what kind of sets do I get if I set this equal to some R? These would be all the possible values. So what points, what monomials are going to have the same order? Well, obviously they all lie on a line, right? Now there's only 3 cases in this simple picture. One case is where the first in a family of parallel lines intersects at this point here. This value is actually going to be the order of phi initial on y to the b. So all these points up here, these will all have order greater than or equal to the order of y to the b on this curve. Now the other possibilities, I think you can see. Another possibility might be that you have a line determined by phi, which hits here. In this case, all of these have order x to the a. And the third case, of course, is the case where the weights that this initial form assigns are the same as the weights of X and Y. And so this last picture looks like this. So these are the monomials. Well, what is the intersection of all three sets of monomials? Well, obviously, the intersection of all three sets of monomials is this one here. This is also the intersection of all three sets. And those, of course, are the monomials where the order of M, well, let's write it this way, where the weight of M is greater than or equal to A times B. Well, that's the proof. And we successfully reduced it to just considerations of a simple combinatorial object with some lines. Well, how about a more complicated example? Again, I can plot the monomials, but I'm going to do a little bit extra this time. I also want to sketch in all the points where, when I add on tuples of positive numbers, all the points I get. So I have this one here, and I have, this is 2, 2. And then I have 0, 5. So in our construction, we first plot monomials in F. So we get Ij plus R2 plus, or in general, it's Rn plus. And then we take the convex hull. And then if I do that, I get something that looks like this. This whole diagram is called the Newton diagram, and this is the Newton boundary. What we would like to do is to get a condition which will guarantee that all the monomials that are on or above the Newton boundary are actually in the integral closure of the ideal. Yeah, so these are also called faces. And here we have 5 faces here. 3 of our faces are vertices, and 2 of our faces are edges. And these are faces. Now I'm going to be looking at each of our faces in turn. We want to look at if I'm given phi mapping C into Cn. In this case, it's just C2, but it could be Cn in general. We can take the monomials on a face and then we can look at the order of phi on those monomials. And then let delta phi is the face where phi has its minimum. It's a little exercise in combinatorics that if the minimum, for example, is on a one-dimensional edge, then it has the same, all the monomials here are going to have the same value. If they didn't, well, then you could bring this a little bit lower and you'd find that perhaps this one was where the minimum was really obtained. Okay. So what we want to have happen, what must happen, is that when we compose phi with the parts of f that are on delta phi, so we need m composed with phi, where m is a monomial on the face that comes from f. And we need that m circle phi is not 0. we need that if I actually use pieces that come from F, that I actually get the value of phi on the face. Well, here is the condition that ensures that. It looks a little strange at first, but not so bad, actually. So we say that F is non-degenerate on the face delta if the part of JF on delta does not vanish So let's try our example out. Maybe I should also say if F is non-degenerate, on all the faces, then F is Newton non-degenerate. Okay. So I'll just do two faces and you can do the rest. I think actually I'll do this one first. I'll do the Newton boundary in yellow. So this is the family of parallel lines that the initial part of phi determines. These are the different values that it has on the monomials. So let's see what happens here. So I want to look at JF restricted to, well, let's say it this way here. We want to look at the monomials of 5x to the fourth plus 2x. And actually, we're going to do things actually a little bit differently here. Instead of using JF, I think I misspoke there. In this game, what we're using actually is ZI partial F with this partial F with respect to ZI again. That's what we're doing. So here, if we look at this thing I just wrote down, that's 5x to the fourth plus 2x squared y squared plus, and that's it. Then the other one looks like 2x squared y squared plus 5y to the fifth. And I only want to look at the part on this vertex here, which I'll call V2. If I restrict to V2, I just get 2x squared y squared twice. Okay. Well, where are the points where this is zero? They're only zero on the axes, right? So there's no points. There's no points in here. So we've checked the condition. This is Newton non-degenerate. And then, well, let's do this one here. Let's call that, this one is going to be edge 2. Okay, so if I just restrict to this yellow segment here, what do these become? How about this one? This is a square here, by the way. Yeah. What's the part of this that's on this yellow edge? The whole thing, right? And the part of this on the yellow edge, we have to get rid of the y term. So our ideal looks like 5x to the 5th, 2x squared y squared, 2x squared y squared. And we see that that is equal to x to the 5th, x squared y squared. Where are the only places where that is 0? On the axes. Actually, for this one we need the x-axis, just the x-axis. So here we see that the vanishing of this is contained in the, its intersection with Cn star is empty. Now, in this example that I did, one of the nice things about it was the boundary of the Newton boundary intersected all of the axes. So if that happens, we say it's fit. And the theorem is that if the Newton boundary of F is fit and F is Newton non-degenerate, contains every monomial above or on the Newton diagram. Okay. Well, we're a little bit over, but just have a minute or two here. Supposing you were trying to do this for modules, what do you think you would wind up doing then? Well, let's just talk about a simpler case where you just have a map. If I have, for example, we use the Newton diagrams of F1 and F2. And then we develop, which I don't have time to do right now, but it's in the paper I wrote with Jim Damon and the Invenciones that came out in around 79, maybe 81, something like that. Anyway, in that paper, no, actually this is different. Sorry, this result I'm quoting here is actually from my Invenciones paper on Whitney equisingularity. But in the Damon paper, the paper I did with Damon, we looked at a lot of machinery for extending that idea. But anyway, getting back to this, we use the Newton diagrams of F1 and F2, and there is a non-degeneracy condition. And the theorem this time is that if H1, H2 are above or on the respective diagrams, then H1, H2 is in the integral closure of the ideal generated by F and this submodule of the Jacobian module, Zi partial F, partial F with respect to Zi. So you can extend all these computations to modules, and the reason it works is because the geometry is strong enough that with the non-degeneracy condition, you can calculate the orders of all the terms you want with respect to any curve. And that's it. Thank you very much. So any questions about what we did today or about anything else in the notes or in the lectures we had last week? Yep. Oh, microphone, huh? Good idea.
Sorry, but I forgot about the microphone. Could you repeat in that ideal, the one with the V2? What are you doing there?
Oh, V2?
Yeah.
Right. So V2 is a segment that goes from the monomial, the point representing the monomial x to the fifth, to the monomial representing x squared, y squared. So I want any monomial on this line that belongs to f, I'm going to use. So I look at the derivatives here, and I see in this derivative, both these monomials are on this line, and so I'm going to use the whole thing. This is E2, yeah, here we go. So I'm going to use the whole thing. Now, from the second one, the only monomial that's on the second edge is this one here, so that's all I use. The idea is that when I compose with phi for this setting where this gave the minimum phi, this will be too high to matter. So we throw it away. Okay, and so then we have this nice situation where this and this simplify, and we have this nice monomial ideal, and we see that we're in business. It's Newton non-degenerate. So actually this, I don't know, did you guys implement this kind of stuff with your program? That is, namely, if I feed you a polynomial, you tell me whether it's Newton non-degenerate or not? No, I'm talking. Not yet. Okay, that's good news. I look forward to that. Once you do that, let's go work on the modules. Okay, any other questions? Well, it's been a long day and it's time for a cerveja, huh?